Welcome everybody. Today we have Mattia Manzati. Mattia has been working sort of in secret for the last whatever
4, 5,
4,
6
5,
months.
6, 6, 7, 8, 9 months on a little project that we
Yeah.
had, which is
Yeah,
not
on a
little
yeah, on a
little
little
is an
weekend
euphemism.
project. Yeah, a little weekend project that took about 6 months, but yeah, a
Yeah.
little weekend project.
And that's supposed to become actually the first layer one infrastructural looking project that we have in the effect organization. Now I'll start by explaining a little bit the problem statement, and then I leave over to Mattia to dissect all the details. The point being is parallelism in JavaScript is kind of a weird thing,
Inexistent.
kind of inexistent, and in general, any form of parallelism that you can get in JavaScript has the same problems that you would find in distributed systems when you have basically a cluster of independent processes that can die, can come back, and
Do
you need a way
whatever.
to kind of orchestrate those, refer to them by name, not by location, because they could be processes spawned everywhere, and you need reliability of processes, you need reliability of persistence, and so on and so forth.
Yeah.
Generally speaking, in effect, we believe layer one infrastructure projects will be very important, and this is kind of the foundation for cluster management, and you see what Mattia
Yeah.
has in mind, and but keep in mind this is layer one. There is going to be layer two things built on top of you being of you having the ability of managing smoothly clusters, which can be
Mm.
both in servers or inside browsers, and so on and so forth. So please, Mattia, I
Yeah.
I'll shut up from now on, and I'll only
No, no,
raise questions from time to time.
yeah, you're very welcome to interact and say whatever, whenever. And so basically, as you said, the problem is that in JavaScript, there's actually no management of concurrent processes. And that means that one thing I always wanted is to try to maximize and speak about system in JavaScript without having all the trouble, all the problem, all the weight of thinking about protocols between systems, or ensuring that all those systems are actually up and running, and all those systems are actually running as they should without interfering with each other. So I'll take a little real world example, and this real world example is actually really connected to what I do at work. At work, I basically work with warehouse management systems. There is always these things. This example you have may seen or 1,000 times, and this example is that if you have two users that are creating orders in your systems, and basically you have system where if there isn't enough stock in your warehouse, you should either reject the order or do something else in order to handle that. And when you work with monolithic application, that is really easy, because usually what you do is wrap everything with a single database transaction, and that's all. Basically, you block everyone until that happens. But unfortunately, with the time passing, with systems changing, even with interoperation of different systems, having a single transaction isn't anymore a real option.
And
And
most
so,
importantly, I would have to mention one peculiar fact about transactions. Uh, a transaction is good only within the boundaries of a single
yeah,
system. You may have
yeah,
one database which is ACID compliant and transactional, but even if you've got two ACID
two database.
compliant databases, uh, ACID compliance transactions don't really compose.
Yeah.
So you cannot have a transaction that spawns two databases, even if they are within themselves perfectly compliant with ACID rules and so on and so
Yeah.
forth. So really, I would have to say that any system ends up being a distributed system.
Yeah.
Even if you're building a simple app in kind of Next.js, and you have a database and you have SendGrid to send out emails for registration, well, that's already two independent systems that you can orchestrate in a transactional manner
Yeah.
directly. So that's already a distributed system, just as
Yeah.
simple as that.
I would also say that as long as you have a user and a database, you already have a system which is distributed, because also the user is an
Also,
actor
the
inside
user
a system.
might be an actor in the system, of course,
Yeah, yeah, exactly. So
or most
basically,
importantly, the user's browsers.
yeah, the user browser is a system. So basically, there isn't any real world situation where you have only one system, where you can have so many guarantees about only one system. So the reality is that we have to deal with multiple systems, and usually that ends up, as I said before, with two different strategies to ensure the system data is in a not a corrupted state due to conspiracy problem. Those solutions usually either involve either having a global lock, which means that somehow you are able
That's the
using
famous stop the word.
yeah, exactly, stop the work, stop the time. I will perform the work just now. Nobody else should work until I tell, yeah, you can resume, you can make the time go again. And as you can find out, that is almost impossible to realize in a real world scenario. Even with whatever you can think of, log files, global transaction logs, whatever, you cannot guarantee that you are able to perform such things of having a global log. And also this skill performance, because this means that as I said, you have to stop the word and perform your work and finally release the lock. Or you can assure that all the work related to an entity, to something, is handled by a single process instances. Basically, you are assuring that whenever you receive a request of writing an order, what you actually do is, instead of processing the instance in that system, you redirect that request to another system, and that system is the only one that will perform the behavior of that order. So, for example, in this scenario, we solve the problem of concurrent orders, because basically the only system that is running our orders is the system number three. And whenever system one or two tries to interact with stock, we'll instead redirect the request to the system three. And that means that we put ourselves in that real world scenario of only one system behaving within a single transaction, be in a situation where basically you are in a happy environment where you can do whatever you want with your entity, because you are sure that that entity
You
only
are the only
lives.
one doing it.
Yeah, they are the only one doing it. Your entity only lives there and nowhere else. And basically that is the premise of
and
what.
I would have to say this approach compared to a global lock actually scales, because
Yeah,
you can uh, kind of transparently allocate different entities in
whatever.
different places and have shard primitives that where you say out of what 10
Yeah, basically.
servers you have 500 different entities allocated, each one doing completely different things, or even the same thing for like processing orders but for two different subsystems that don't collide between each other. For example, I'm I'm thinking I had the same troubles when I was developing trading platforms, and you've got a lot of instruments, and orders are usually per instrument. So you would have your entities defined as the single instruments, and your users would interact with those entities. But if you both traded the same instruments, you ended up in the same single writer that managed
Yeah.
that specific instrument.
Yeah.
We were doing so in Scala and in the JVM. So it's
Yeah.
kind of curious now, the ability of doing it across systems in TypeScript with effect is just amazing.
Yeah, and that is also really awesome because as I can see here, I wrote systems. So since we are running TypeScript and Effect, so basically JavaScript, uh, that thing that you said about running Scala in the backend is not so true here because nobody says that these systems cannot be the browser and this system tree can be a background worker. So basically, you can have your user interface interacting or multiple tabs of the same browser interacting with a single worker behind the scene, doing actually all the state management, all the writes, all the API interaction. So as you can see, running with distributed systems is actually a problem everywhere. Backend, front end, API interaction, whatever.
Especially if you get to more kind of edgy architectures, like you want your app to work offline. Well,
Yeah,
if you want your app to work offline, you're better off thinking in a local first manner, which in simple words end up meaning running a database locally,
yeah,
which is exactly one of those systems that could propagate state, manage state, and so on and so forth. I can kind of think about a common friend we have. She's also an effect power user that would enjoy using this system a lot.
yeah,
I'm of course calling Johannes Schickling, which is building Overton as a local first app, and using actually a lot of workers to off shift
yeah,
intensive tasks and stuff like that. Kind of a
yeah,
year ago, I was telling him, buddy, you are actually developing a distributed system inside your browser. I was like, yeah,
yeah.
that's that's
That's so
that's the
true.
first time I'm seeing it. But if you want your app to work beautifully and fast, that's actually a smart way. It's actually a very smart way.
Yeah. And that's so smart also because you relieve so much the user interface thread. So basically, you perform all the heavy work in the backend, and the user interface is just interacting with those external systems. So either those systems are running on a remote server or running in a worker,
Doesn't really
and
matter.
does not really matter, right? You are just interacting with systems,
Yeah, you may
and
have a little like it's up to serialization, because of
yeah,
course if you
exactly.
are running in a worker's environment, then you might be able to share, for example, byte buffers
Yeah,
or other stuff. And if you're not in that environment, you may not.
yeah.
But as we will
In the
see
end,
later on, it's all pluggable. So
yeah, exactly. And so basically, this is what we are trying to solve with Shardcake. And this is inspired by our original Scala library from the Zio community by the sisters. But we plan to integrate more behaviors, more things inside of what Shardcake does. But what we already accomplished is that single writer approach. Basically, with Shardcake, you can ensure that each entity is running only one time in one place, as we said before. And the other nice thing is that you can communicate with entities with just knowing their ID. So, as I said before, knowing if that API is running on one server or another or in a web worker actually doesn't matter. As long as you know the ID of the entity you want to interact to, that's enough. You can create a communication with that entity as long obviously there is network connection between those entities trying to
provided
communicate
that they communicate.
But well, that's
We have still
uh,
not solved physical boundaries.
yeah, exactly. We are trying to, but well, that's a harder problem that we can tackle. And these two basic things actually end up solving a lot of problems. And
Because
how
they are
we
kind of two fundamental primitives.
yeah, exactly. And basically, once you can ensure that a person can be only in one place at a time. So basically, that's the single writer, and you know the ID of that person, so you can interact with that person by just knowing that ID. You have enough because with that you can build whatever behavior you want. And before going to having a dive in what we accomplished, having a simple example, I want just to put some keywords because when I approached this word, I had some trouble fully understand these keywords. So entity when I say entity, basically I say a behavior. So we have the user entity, which is the behavior of how a user accepts messages and perform its works and maybe replies to other entities, or a to-do entity, which basically have a to-do behavior. So basically with the entity is the behavior defines how an entity behaves in the system. And
And fundamentally, you can have instances of entities. So
exactly, exactly,
individual invocations that behave according to the specific behavior. If we kind
exactly,
of want a mental model, that's a class versus the object created
exactly,
class.
exactly.
That's probably the most similar concept
Yeah,
that we can find at a
yeah,
higher
exactly.
level, because again, this is not a local class; it's kind of a distributed
Yeah,
and automatically
exactly.
allocated class.
Yeah, and also there is this pod concept, and basically, what a pod is a pod is, you can say, a process, but basically a pod is something hosting the instances of those entities we defined before. So basically, in analogy, is the server is the process running the behavior, and we have this concept of shard. And basically, the shard is a grouping of instances of entities. So basically, we can have a entity be a part of a shard, and the shard maybe run inside of a pod.
So
And
pod ends up hosting shards in
exactly,
strict sense, not directly
yeah,
instances, but shards that each shard hosts a number of instances of entities.
exactly, exactly. And that relation is called assignments. So basically, the correlation between the pod and the shard, and knowing in which pod is running a particular shard, so a particular group of entities, is called assignments. And those assignments are decided by a shard manager, and the shard manager has basically the job of supervising the pods and ensuring the pods are alive. And if some pods is not alive, it performs again the work of assignments, so it will decide which group of entities should run where in which pod, and basically rebalances the system as the system topology changes. You can think about that. I think that this is the simplest way I can define that the work that the shard manager does.
And most
Okay.
importantly, again, this is a single instance, but
Yeah.
it has to manage the assignments between pods and shards,
Yeah.
not between entities themselves.
Yeah.
So it means even without the coordinator running, as long as there are no fundamental changes in the topology,
Yeah.
like you can't add new nodes and you
Yeah.
cannot rebalance nodes if one is down, but
But the
as long
system.
as anything stays the same, the system is operational.
Yeah.
And if not, it's only partially not operational, because like you may have a node down and some entities are not running, but the other 95% of entities will be running
Yeah.
just fine. So
Yeah.
that's similar to a design that we now know in VPNs. I'm very passionate about Tailscale, which is kind of based on WireGuard, but it's a VPN where if the coordinator is down, you communicate peer to peer between nodes. So it's like, yeah, it doesn't really make sense to distribute the coordinator further because it's actually a perfect job for a single. By paradox, it's another usage of the single writer principle.
Mm,
The shard
mm.
manager in itself, it's should be instantiated in one place.
Yeah, and one place and one only. And also, what's really great is that having a single shard manager also prevents problems, and like, um, if you had multiple shard manager, you have collision about the assignments entities that should I run on that pod as shard manager one said, or on the other like shard manager two said. And there are problems related to that. And the shard manager is also so dumb in the implementation that it takes milliseconds to start. And so, as you said, even if it fails, the system will continue to behave, and you will have it will take so small time to go up again that you may even don't feel that the shard manager full.
And most
Because
importantly, it's another pluggable part of the system, so nobody
yeah,
actually forbids to, in the future, like develop one shard manager on top of etcd and have
yeah,
a small cluster if one wishes to deploy something like etcd or zookeeper or other
yeah,
sort of databases that are made to orchestrate one. Like I
yeah,
can think of Kafka. Initially they had
yeah,
it's similar in some sense. And initially they had a zookeeper, now they're doing internal paxos, but still you've got one system that is dedicated to allocating shards. The reliability and consistency of that system, again, that cannot be high throughput.
mm,
That's the limitation on the single thing. But if you don't need high throughput, and with a system like that you literally don't, you
yeah.
can you can manage the shard manager very very well in probably 100 different ways in the future.
Yeah, also because thinking about it in this context, you really will not have so many servers or pods going up and down continuously. So yeah,
That's the point. The
yeah,
complexity of the shard manager is pod versus shards, not pod versus entities.
entities. Yeah, yeah. And basically, how it works, well, as we said before, we have the shard manager, which basically is the single entity that a single process that is running, and the shard manager to the pod's API will basically assign and assign to each pod or application server the assignment of which shard should be run. And both the shard manager and the various application server pods will have their own storage. So basically, each pod has a local cache of the assignments of the entire network. And so, in the case that the shard manager goes down, the local cache will be fine enough to continue to the pod work and interact with all the other pods and the entities in the system. And there's also an optional pod health API that, as you mentioned before, if you have systems where for example, your shard manager is running on top of Kubernetes or whatever other instances where you can programmatically know the status of a particular pod, a particular server, if it has too much work, if CPU is almost bound, a situation like that, you can provide an API that basically will tell the shard manager, consider that server as it is almost dead. So do not even try to assign new pod, new shards,
And potentially
and
drain some
yeah,
shards out of that pod.
yeah, exactly. It try to get some relief to the pot. So basically, all the system tries to stay balanced even in the work. And these shapes that are of different color are actually different services inside of our code. Thanks to effect in its pluggability, the serialization is completely pluggable. So, for example, now we relive on basic JSON serialization thanks to FX schema, but nobody forbids that someday someone implements something based on gRPC, for example. And for example, also storage. Up to now I implemented three different storages just to make try the system and ensure that it actually works. And those systems are in memory, or for example a file-based system where I use files as storage. If you have only one server, for example, and different processes, that's enough. And also an SQLite implementation that I'm trying to evolve into a real world database implementation for storage. But real world application will have something like Redis, for example. Uh, and
Redis, a Postgres, a
yeah,
Cassandra,
yeah, whatever.
like as long as you can store blobs of stuff indexed by
Yeah,
key, that should be
yeah.
enough.
Yeah. Basically, the requirement is that you can store and you can also get update from the database, because
Or
this
you
part
can
of the
pull the
store.
database for updates.
Yeah, exactly, exactly. Because in the eventual case that the shard manager or the application server are not, for some network issues, are not able to directly communicate, but the storage can. What will happen is that as a fallback, the shard manager will directly write the assignment in the database, and every pod will watch that assignment changes and actually pull directly from the storage. That is a second fallback that the system does just in case for some network issues
And
the direct communication
how
don't work.
does the assignment work?
uh,
Because
the ass-
to be able to deassign, you've got to have a confirmation that either the pod
basically
no longer exists or that the actual shard has
basically
deallocated before you assign it again.
Yeah, basically it won't deassign. What it will do, it will update its internal cache, and its internal cache is what the system will try to use when try to interact with another pod. So basically, what will happen is that if, for an example, the shard manager goes down, okay, but you get an update from the storage, okay, you get to remember that the only writer into the storage is the shard manager, so you can ensure that the assignment that got written into the storage are correct. And if they are wrote in the storage, they are wrote in the storage because the shard manager actually ensured that the shard is completely full when assigned from the pod. Okay.
But the shard manager checks that
Yeah. Yeah.
the shard has been deassigned,
Yeah. Exactly. We'll perform that only if the shard is completely unassigned.
or the pod is
Okay.
considered that.
Or yeah, or the pod is completely down, so that means that there is actually no shard assigned to that pod. Okay. Okay, so I think that now we can have a dive into the code, maybe.
Yep.
Okay, so I'll just a second, I'll switch into. Okay. Okay, so just a second for it to warm up. Okay. Okay, so I think that we can start by having a look at a simple example of how the library can be used. And we start by saying that basically, as we said before, the first thing we have to do is define entities, define behaviors. And in order to define a behavior, the first thing you have to do is actually define a protocol for that behavior. So basically, the list of incoming messages that the behavior will handle, and eventually the list of responses that that behavior can emit. So here, for example, we have a counter behavior, and this counter, as you can see, is powered by FX schema. So we define the protocol using FX schema. What we will do basically is create an union of all the possible incoming messages. So as you
And
can see,
can you show me a
yeah,
little for a second? Close this window for a moment.
yeah,
When you do message.schema, what
yeah.
are you getting back?
Okay, so
Because I
before
see
going,
two things called get current.
yeah, exactly. I get two things back. One is the schema
Okay.
that gets injected a replier, so basically where the reply will be stored, okay, and where the function call for posting the PRI to back to the sender. And the second is just an utility. It's basically a constructor function that, given all the data is required by the message except the replier, and given the reply ID that needs to be constructed inside by Sharding, will create the complete message that will run over the wire.
It might be worth to have a subtype of schema called like message, where you
Yeah,
store both of the things in the same object structure. So you
it
have
it,
get current
it
and get current dot.
yeah, it may be worth. The challenge is that this reply ID actually gets injected only when you actually send the message. So the challenge here is that you can
I'm
effectively
basically saying have this get current as a function of the schema. Just that.
of a yeah, that may be a good idea. I would think that
So
we
you have
can
a single
experiment here.
object instead of the
Yeah,
tuple,
yeah,
the tuple you
yeah,
have to spread.
yeah, exactly.
So you
We can
say
join both
export
together.
const. Yeah,
Yeah,
precisely.
yeah. You can both join together. Yeah, that could be something. Basically, have schema with a constructor. Yeah, yeah, exactly. And here we define the messages. These are messages that are send only. Basically, you send those messages and you don't have any kind of reply. And here instead, those you pointed out are two different kind of messages. One is a message schema, and a message schema basically only has a single reply. Quindi given the get current count request, I can only reply with a number. And this is instead another kind of message, is a stream message. And this, instead of having replier, has a stream replier. So basically what happens is that when sending the message to the entity, you will get back a stream, and basically in that stream the entity on the remote pod will push values, and you can consume values on the caller side. So basically, you have things like subscription in this case, or whatever you want, basically on streams, and that's actually really neat because this specific part of streaming responses is one that I really love a lot, and I think is missing in a lot of systems. And
Again, those
that's really,
subscription can be, for example, HTTP push events,
yeah,
WebSockets.
whatever. Basically, right now it handles any FX stream. So basically, by having a FX stream, you can then model whatever you want. Like you said, for example, you can consume that stream and publish that into a WebSocket, or like the actual real world implementation does, it use server side sent event in order to once you post the message to the remote pod, you get back basically a streaming response of whatever comes back. And with this, basically, you define the protocol, you define the entity, the behavior. And as you can see, we have make entity type, Why we say entity type? Because actually we also have other types of entity. We have also a topic type, and a topic type is kind of a topic where multiple entities, multiple subscribers can subscribe to and push to, and basically you then broadcast. And entity type instead is what we thought up to now, and basically we have the concept of an entity running only on a single pod, etc. And here we define basically the entire protocol of our entity. Then we start actually registering the entity behavior, because now, given that counter entity that we defined before and we have only the protocol of the entity, we actually implement the behavior of the entity. And the behavior is actually defined by a really simple signature. Basically, this signature of the behavior is that, given the entity ID, because as we said before, for a behavior we may have multiple instances. So basically, this is the instance ID, and we will get the queue. And that the queue, basically we will pull for all the messages that will be put there by other entities or whatever is trying to interact with our system. And one thing that I want to also to note is that in that the queue we also get this poison pill, and basically this poison pill is put by the system when he tries to shut down an entity, because you can specify when you register an entity behavior also things like uh, if this entity doesn't receive any message for 5 minutes, you can assure that this entity can be shut down in order to avoid consume too much memory or things like that. Or you can force shutdown of an entity, and that message is put here instead of using regular effect termination or interrupt, so that we can actually perform a fully clean interruption of the behavior. So basically, we can also ensure that you can have behaviors such as end up consuming all the messages that are in the queue and then shut down. So ensuring that you actually reply to askers that asked before you shutting down and things like that. And this is really great because this is very pluggable. So having the behavior defined as this allows you to actually define then combinator that consume this the queue and perform the behavior whatever you want. So the most of the times what you will do is basically try to take from that the queue. And here we have a simple combinator that basically what does behind the scene is just queue.take. It will take from the queue.
Yeah,
And
yes,
if
filter off
and if
basically.
that message is a poison pill, what will happen is that it will interrupt the effect, so it will shut down, and then we have the message, and then we handle the message. For example, when we get an increment, we upgrade, we increment our counter, we decrement. When we get current, what happens? In order to reply to the message, we have that replier that we have seen before, and inside that replier we have the reply method. And basically, with the reply method, we get back an effect, well, where we will send back the response to our client, to our requester. And same goes for replying with a stream. So basically, we have a reply, and then, for example, here I reply with the stream changes of my subscription ref of the changes. And basically, this is how simple you can behave, will define your behavior. And then you define your behavior, but how can I interact with a behavior? Well, in order to interact a behavior, first thing you need to set up the connection to the sharding, basically. The connection to the sharding system that, as we have said before, the system is completely pluggable. So all those layers we discussed before can be interchanged with different configuration of different behavior or different implementation. And then one simple example here that is still written with the syntax. But for example, here we first create a messenger. So basically, we get a messenger that is able to interact with a counter entity. And then when we have our messenger, we send, for example, a messenger, so send stream. We send and subscribe to the reply stream of changes. So here is the reply of changes. Or the most simple use case is that we send a message and we don't care about the reply, so we send this card, and we need to specify obviously the instance we want to interact with and the message we wanted to send. Or sometimes we want to get back the actual result of the replier. So what we do is basically messenger.send again the entity ID we want to interact with and the message we want. And here you can see that that helper gets nice because you get everything already typed out as you want. And finally, you get back, obviously, our number. And well,
And for example,
the
here we could also compact probably the send API,
yeah,
given that in the message we already know if there is a replier or if there is no replier.
yeah,
We
exactly.
already know if it's a stream or not,
Yeah,
and we could just have a send function that returns either a stream or an effect, or so
yeah,
on and so forth. Yeah,
yeah, whatever.
that's very
Yeah,
nice.
yeah, and whatever. We now we have defined our protocol. We have defined our behavior, and we defined the code that wants to interact with our entity. And well, the last thing you need to do is basically create the shard manager. And the shard manager, as said before, is not something like a process or something that you need to install on a server, but is poorly effect and is completely effect native. So basically, it's something that you can actually embed inside of your application. And what basically does it provides some HTTP API, and all the shards need to know the address of the shard manager in order to interact with those API. So maybe if you don't have any question, maybe we can see this example running.
We should definitely see that example, right?
First thing we start the sample manager.
Have you
It
built?
is ideally yes.
Indeed, yes.
We will see.
Oh, that's running test notes, so that shouldn't be
Yeah,
necessary.
exactly. Yeah. Yeah, it uses the compiled build of the library, but it compiles on the fly the example. Okay. So as you can see here, I have full logging enabled. So we can see that the shell manager has loaded and now is listening on HTTP port 8080. And now we start another process. And this process, we start sample shard. And sample shard is basically the pod that will run our shards. And here, the first thing that you will see happen, as we have seen before in our little diagram on how the system behaves, is that now the pod will start its own on its own port the API that allows other pods to communicate with these pods. So basically, receive message and reply to the messages. And but also will register itself to the shard manager. And what happened if we go back to the shard manager? We can see that all this long string that we see in the console is basically the list of the shards that got assigned to our pod. And basically, we can see that the pod has registered, and since the pod has registered, the topology of the network changed because before we haven't got any pod, and now we have. And so the shard manager started a rebalancing process, and inside the rebalancing process is so that the only node is that pod, so basically assigned all the shards to that pod. And now one other thing that we can do is basically run the sample connect. And the sample connect is an example of a process that
It's
is
going to
connected. Yeah, is
interact with the entities.
Yeah, exactly. It's going not to be an active pod of the system, because you can also have nodes that aren't active pod of the system, but can only register into the system and interact with the system. For example, I usually think that API gateway or something like that maybe can be an example of these kind of scenarios where you have some kind of processes that are part of the sharding, but are not hosting entities. So need to know how to interact with the entities, but will not host any entities. So here we'll see that, as we can see before, I was logging every time there was a subscription change of our counter, and we finally called get current to get the current value of the counter. Current count is 2. And if you remember in the behavior, I had a log saying basically counter is now, and logging each time a message got in the current value of the counter. And you can see that that is logged on the pod process, not on the connect instance. So basically, we interacted with different processes. And ideally, if I am quick enough to restart again our sample connect before the entity will be automatically shut down due to interactive time, you can see that now it received again increase. So you go 3, 4, and now it's 4. And even if I shut down my connect, the entity is living inside the pod. So that's really nice. That's really, for
And
me,
clearly, this is not yet persistent in the
yeah,
sense that the state we are keeping it in memory with a subscription ref.
yeah,
But these
exactly.
days, you could store that state in any database you want. When the
Yeah,
entity comes up, restore the state from the database, or when the entity updates, literally write to the database and
yeah.
publish back.
Basically, this gives you all the basic tools to have the behavior, have the location transparency. In this userland code, you write something like this, where you actually don't care where the entity is running or how to interact with the entity. All is taken care by Shardcake. And what you will actually take care of is things like you said, for example, how to persist the state, right? But even into that, as I said when starting the stream, we are planning to extend the functionalities of Shardcake and also include some persistent behaviors, such as event source behaviors or behaviors that actually store snapshots of the state. And well, there's a lot of work to be done, but something is already has been done. And also in this system, there are also already built in other things, like for example, singletons. For example, you can define a process that should be always up and running, and with singleton, you basically can maybe take a look
Think of
on.
it, for example, like distributed cron tabs or stuff like that.
Yeah, exactly.
The easiest
Or
way is
some,
have a single process that does the cron tab and communicates to the rest.
yeah, or if you have something that needs to continuously pull from external systems, well, that exactly an example of singleton. Basically, a singleton, you need to give an ID of the singleton, and then you define the behavior of the singleton. For example, here in the test, what I do is just complete a deferred, but here in will be the effect that, as we said before, will, for example, pull or
This is a thing
subscribe
that
or do
never
whatever.
terminates.
Yeah, exactly.
And
Basically, is
it maps to an effect fiber, which is running in some pods, basically.
yeah, exactly, exactly,
Well, not in
exactly.
some pods, but in exactly one pod.
Exactly one pod, exactly. And by default is the pod number one, but you can change also that. So basically, you can ensure that is running always in a particular pod. And I'd say that maybe if there are no other question, we can move to see another example. Oops.
I think we can switch to the
Yeah.
persistent example with a bit of event
Yeah.
sourcing.
Yeah.
Okay.
Okay. So basically, what I am also experimenting is that, as I said before, that behavior of having I need defining behavior to an identifier at the queue and providing that an effect that basically pulls messages from the queue is so basic and is so powerful that allows, as we said before, to do whatever we want based on that, just by just composing that signature. And for example, what I'm also experimenting with
Just
is that,
one small
yeah,
piece of in that code. If you go back to that code, because probably
yeah,
this was written before we made the
uh,
generator.
yeah, I don't remember where I was and which file I was before.
This one,
Yeah, okay, yeah.
you've got a yield
Yeah,
with a pipe in it. You can
yeah, yeah,
remove
yeah.
the pipe.
Yeah, that that was yeah. I am a so long time in effect user that or sometimes I miss all the fancy new things that happens. And I'm still attend to the old adapter, well,
Which took a
that
single
pipe.
argument.
Yeah, took a single argument. Yeah, exactly. And back to what we were saying. Oh yes, here basically we can also experiment with different type of behavior. For example, an ever sourced one, and the ever sourced one is very similar to the one we had before, where we still have the messages increment, decrement, get current, subscribe count, but what we also
Because
have,
the protocol of communication doesn't really care if it's event sourced or
yeah,
not.
yeah, that means that the protocol is still the same. Basically, we are only changing the internal behavior of the entity, but for the outside world, it still have to interact with pushing messages. And what changes is that we have an event sourced behavior, so we also need to define events. For example, we define that the counter has incremented or the counter has decremented, and then we define an event sourced behavior by combining the protocol with the events that can be raised by that entity. So basically, we tie that together. And finally, we define the behavior with a combinator that, given the protocol and the events that can be raised, we define the initial state of the counter, which basically is 0, and we receive the new comments. Here we have the union of the comments, and based on the command and the current state of the entity, we can decide if we want to emit new events or not. Maybe there are commands like increment or decrement that change the value of the counter, so they emit events, or messages that just read the state and reply back to the caller, for example, get current or subscribe count. And then those events that are emitted are then folded, and the current state is then created by folding those events. And what gets really interesting is that with that signature, we can do basic persistence. And if we persist basically the information of the event that occurred and the ID of the entity, for example, I implemented SQLite as a simple persistent mechanism, and we can see that I have a simple table, event journal, where I store basically the sequence on the order of the event that happened, the type of entity, and the ID. And you can see here that we have basically the serialization of the events that occurred. And now if I try to restart my behavior, what happens is that before accepting new messages, the entity will basically replay all those events and basically recreate its internal state by
And again,
calling this.
later on you could do snapshotting and so on and so
Yeah,
forth.
exactly, exactly. Snapshotting basically is an optimization where we will truncate at some time the event log, and before that you before interact with the snapshotting. But as said before, it is currently a lot is ongoing, a lot is still to be have performed, but a lot is already working. So that's the spot or where things got interesting, where you have a system that is kind of working, but you want to experiment basically what is capable to do. And what you said is really interesting. You can also have snapshotting, for example, and here we have already have persistent behavior. So basically, you can write an application that only persists its events and snapshot and is not tied to the shape of the
This is
database
basically
or whatever.
a distributed Redux on steroids to some
Yeah,
extent.
exactly, exactly, exactly. It is distributed for users like me that back in the days used um, Redux with some persistent plugins that basically every time the state changes, put
You're
the entire
persisting
state
it.
in yeah, persisting it in local storage or whatever. Basically, this is it. This is it, but this is built in with Effect, so you get all the nice things that Effect does.
And most
And
importantly, you have a distributed orchestrator, which
yeah,
you kind
exactly.
of did not have with Redux and
Yeah,
persistence.
yeah, exactly.
It looks
uh,
like that, but this
yeah,
gets executed in a cluster where you reference entities by ID, and
yeah,
again, you don't care where they are
yeah,
allocated.
yeah. And there are really, really, really thousands of things that can be built on top of this. And for example, I also started working on something that now you have entities that emit events. So now maybe it's time to also have some logic coordinator, some process manager. So I'm also starting to work on something based on that. And to my surprise, I also find out that basically any process is just an entity itself. So basically, you find out that this simple abstraction is so powerful that once you know that you can interact with everything by just knowing its ID, and you can ensure that that is running only in one place, jackpot.
Yeah,
And
that's already a lot, because then a
yeah,
lot of patterns arise naturally from that. Because again,
yeah,
like a Saga orchestrator or a thing like that, yeah, you will
yeah,
have
whatever.
one process that is responsible for the orchestration of
Yeah,
specific
exactly.
things.
Yeah, exactly. For example, the way I'm starting to implement that is basically
But
I
can you
put
maybe show on the sample connect example
yeah.
how do
Well,
you,
yeah, right. Excellent.
because that's just the behavior, but
Yeah, exactly. That's the behavior. Uh, we have obviously the creation of the sharding system. Here, for example, like creating an
just
in-memory shard, an
basically
in-memory
the same
sharding.
type of configuration that we saw before, plus
Yeah,
some
exactly.
persistence related config maybe.
Yeah, exactly. And here we have the protocol, as we said, we have seen before, the behavior, and final we define our program. When we define our program, first thing that we do is we register our entity. Basically, we define that the sample entity is handled by this behavior, and I also put a configuration where I said that after half a second, if there are no incoming messages, I want to shut down the entity. And we register the sharding. So basically, this register scope call is what will eventually register this pod to the shard manager. And then we get the messenger. So we get a messenger able to communicate with increment, decrement, all the messages. We also start in a separate fiber a changes subscription that will log the changes and in a separate fiber. and then I send an increment of 10, a decrement of 10 without caring of actual response. Also an example of a request where I send a message and I want to get back a result. Current is a number. Then just for the artifact of seeing the process, the entity stopping, I see here, for example, that I sleep for 1 second. So that basically times out our entity. And then I send again a message after that, and to ensure that basically the behavior replied correctly the events and get the current value of the events. And then finally, we have all the layer we need to provide. For example, here we have memory sharding, the event store as a SQLite implementation, serialization, set the log level, etc. And
And
this
again,
event
just
store,
those could be packed on the main layer, having a
yeah, exactly,
single thing to
yeah,
provide.
yeah, yeah, yeah. Yeah, basically that is built on another services that is required. That is the event store, and basically this event store is that another service. So basically,
Which could be
whatever.
implemented in wherever
Yeah,
storage
exactly.
provider you want.
Yeah, exactly. For example, here this is implemented both in memory. I have an in-memory one that is baked by RF, or the actual one which is baked by um,
SQLite, yeah.
SQLite. Yeah, you can see I performs. Yeah, up to now I don't support snapshot at the moment, so basically I just do three basic methods that are read stream, that basically for an entity, for a specific entity, starting from a specific versions or a specific state in the time of the life of the entity, I get back all the events that
Well,
occurred.
in theory, the snapshot store could even be a separated interface,
Yeah, exactly,
because
exactly. And
the event store just has the primitive to read from
yeah,
a
to read
place to
from,
another.
yeah, for it to the event stream basically and persist the event in the event stream. I've also added the ability to read the entire journal starting from a single point in time. And that's nice because if you have process manager or things that needs to subscribe basically to every event or event inside the system, that's nice. That's not the standard way you would want to do that, but I think that is, you know, then that's admissible, that possible, that doesn't do nothing bad inside our system. And basically here is what we will have to expand on in future days, because right now what we have is the behavior, the shared transparency, the messaging. What we are actually just missing is basically mm,
All the
whatever you,
different
yeah,
the different
yeah,
standard behaviors that we could have. For
yeah,
example, one of
and
the most useful that I have found in past experience is to sort of use event storage, but in a non-traditional way, where basically you always store an updated version of the state in the database, so you never end up
mm,
having to reply. The only
mhm,
moment you would reply is when you want to do version upgrading, and you could
mm,
potentially even run two parallel things, one subscribing to the work of the other. But for example, I could then, with this model, I could leverage a single ACID compliant database, have a
mm,
table for the event storage, and my database was the state of the application, and everything was getting updated perfectly. And I had transactional guarantees between state, and because the one of the key problems with having everything separated is the only place you can trust for the state of something is the single writer. It's
yeah,
not very efficient to ask to the single writer for current state. You would want, in some scenarios, only some parts of queries going directly to the writer, and some part of queries to go off the read read systems, but you don't have any guarantee that the read system is up to date
Yeah.
with the single writer.
Yeah. It may
If you use
be
an ACID
back.
compliant database and you have guarantees between a snapshot of the state and the events, you know you're only querying always the latest
Yeah.
thing. And for some problems, that was the obvious solution. I can
Yeah.
remember, for example, a lot of people speaking about users and emails. You gotta have
Yeah.
a unique email and a unique user, but
Yeah.
a
Yeah.
user is allowed to change email.
Yeah.
So unless you
How
put
do you ensure? Yeah.
unless you put all the users and all the emails in a single writer
Yeah.
for the entirety of your system, which maybe is likely too complicated, or you use a normal ACID compliant database and store
Yeah.
current state. So if one user takes an email, the same another aggregate doesn't it's not able to take the same email. So
Yeah.
the transactional boundaries you flex them. And having a pluggable system, we have a way of easily kind of shift those things without really changing code. Because
Mm.
from the usage perspective here, there's nothing that talks about persistence, even
Yeah.
event
Yeah.
sourcing or anything else. That's
Yeah.
just communicating via
Yeah.
messages to
Yeah. Just sending
actors or
messages to.
fibers.
Yeah. Exactly. Exactly.
It's a very
And
simple mental model.
yeah, the more time passes, the more I find out that basically everything is an actor.
To
And
some extent, yeah. But the
yeah,
realization was an actor is actually a fiber with a Q and a pool.
exactly, exactly, exactly. And so basically, in the end, everything is just an identity that receives something.
Well, that is nice.
Well, see, yeah,
And
there
again,
is.
we do plan to make this an official part of the organization, so it gets maintained, it gets extended, and so on and so forth. We did expect to have this a few months ago, but at some
Yeah.
point we thought this was 1 week away from working, and
Yeah.
and apparently it ended up taking a little longer. But
Estimates in information technology works like that, no?
yeah, it doesn't really matter. But I mean,
Well,
we're not in any rush, and one of the goals for anything in the effect organization is we only put it there when we actually know works, when we actually know it's gonna have a future. There's a lot of
yeah,
experimentation behind the scenes, and this is not the first iteration we go through with this
yeah,
with this project.
yeah, exactly. There's also a lot of nice things that, for example, as I said, this started as an inspiration of uh, Shardcake from the Scala world. And what happens is that also by writing it in TypeScript, I find out problems or edge case situation that also existed in the real original Shardcake. So that a system is never fully complete, you know.
Yeah, but
But
but we figured out,
well,
even with the fact that having it wrote in two languages is actually a good
yeah,
way of figuring edge cases.
yeah, exactly. It's kind of a next level of writing tests. You write a system, you write tests for that, and then you write that system in another language and find out the
With
problem you had in
further
the first one.
tests.
Exactly,
But
exactly.
I see other stuff there. For example, workflows. You were mentioning you are starting to experiment. Given now we have a persistent thing.
Yeah, I'm starting to working on that. It's not actually working right now, but basically the idea is that
Is it
now
a week
that
away?
we maybe maybe I'm a little more.
The same terms
Basically,
of the week on.
no, 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 not in the same thing. Maybe a day of that week.
Okay.
So because basically here I said that now that we have the concept of behavior of an entity, and now I can define a workflow basically as something that consumes event and eventually produce new events to be sent by those that got consumed. So here I'm looking for an implementation of workflows that is basically based on generators. Basically, the idea, the API that I'm looking for is something like, for example, const workflow function. I'm looking something like I define a generator, and then I want something like while yield star take, and I want to take an event of type user created. When the user got created, maybe I want to this to saving the event equals. I want to keep a syntax like that. When then I want to yield star put, and I want to send a specific to a specific entity. For example, to do one tag. I want
This is
to.
basically an if then that pattern
Exactly, exactly.
system.
I want to give an if that in then that based on generators, and that's I want to keep that based on generators because uh, first that generators have a syntax that allows to suspend, and this kind of suspension is different from the effect suspension. I want to support an effect in this kind of definition, like effect does .gen does, but I also want to have some kind of signal that is I suspended the workflow because I'm waiting for an external event, something happening in the external system. And in order to achieve that kind of syntax, the first thing that I need to achieve is that I need to ensure that this can be defined as behavior, and this behavior will run inside an entity, and that entity will have the um, will basically have the requirement of that entity receiving all the events of the entire system in order. Maybe if not in order, the behavior need to know when to wait for order to happen. And also that means that I have to have a singleton in my system that pulls from the event stored in events and define the activation rules for when an instance of this workflow need to be activated. So there's a lot of things that mm, comes out from that requirement. And up to now, I just implemented, and it kind of works. The part, well, basically, you define a workflow by giving it a name, what kind of entity events it watches, and you have an activation rule that is basically when I receive this kind of message, I can create an instance of a specific kind of workflow instance, and
That's
then
like
I
returning an identifier for the
the
workflow.
workflow. Yeah, exactly, exactly. That gets great. That I call that activation because ideally, this will be the activation condition of the workflow. But if will happen, for example, that that same event will be triggered again, and you get back the same instance of the workflow, nothing will happen because you will end up sending again the same event to the same workflow, and the workflow will know that you already received that event, so we'll skip that event. There are
Again,
mostly
here workflow really means kind of Saga, basically.
yeah, exactly, exactly, exactly. It's mostly Saga. It's mostly Saga.
Maybe a better name would be a Saga.
Sorry.
Maybe a better name would be Saga of a
Yeah,
message.
exactly. Yeah, exactly. And then you have the singleton that you need to inject that needs to read the journal, and that gets a binary event. I need to know if that specific workflow is watching or waiting for that specific kind of event, and this is the first write that I did of that workflow, that Saga. So this is the first implementation, will be probably changed a lot
Yeah, I mean, of
during.
course.
Yeah, because I also thought about not having an activation, because if you think about it, you can define the activation inside another Saga itself. So maybe you don't need activation, you can just have something that is guaranteed to receive the entity, all
Well, I
the all
mean,
the events, and maybe that will spawn new sagas, and then you register those sagas to receive all the events.
to an
There are
extent,
lots
this
of.
is this is just another type of actor where basically
Yeah, exactly.
you have you, you create it by ID. You create
Yeah,
a
exactly.
new saga ID, and you say, okay, this saga is gonna watch on those
This,
specific
this, this is.
entities, and you just need to specify the entities, not to have it listen to the whole world of
Yeah,
events, but
yeah,
you specify matching entities, and that's it.
yeah, yeah.
This
This
is
is what.
mostly for peculiar event sourced systems,
Yeah, yeah.
but it might be helpful even for simple coordination of.
Actually, I
You kind of
subscribed
do
to.
need to have events, though.
Sorry.
You do need to have events for this to work. Yeah.
Yeah, I was just saying. I was just about to say that I am actually I'm subscribing to an event store, but now that I am saying it loud, maybe this can just be a topic
I
inside
was about to
of.
say, yeah.
Yeah, and I can subscribe to a topic, and I can have a singleton maybe that upon starting ensure that all the past events are published again to the topic. So if someone missed the events on the topic, you know, or some kind of behavior that if an entity a workflow starts and figures out that he received an event way up before what he expects. So for example, he received the event with sequence 10 but he is stuck with 5. Maybe he wants to get what happened before. The only requirements actually is getting events and getting ordered events, I think.
Yeah.
Nothing more, actually.
But ordered events, I mean, they should. You can't have really ordering guarantees across entity types unless you store
Yeah,
everything in a single
yeah,
event store.
I, yeah. I mean, order in a sense that not completely out of time, because if, well, maybe you can actually have them out of order. The thing is that then in your workflow implementation, you don't have the guarantee that they are in the correct order. And well, you will always assume that you can have the correct order for the same entity but not across different entities. Well, that's okay. Well, yeah, it's kind of it's worth an entire discussion, because it's true that you cannot guarantee ordering between different entities, because as you pointed out are different systems. But if you, for example, are interested in events of two different entities, at least you need to ensure that inside the stream of the events there aren't inconsistencies of a single entities. So okay, you are getting the stream of different events, but at least the events of the same entities could arrive in the correct order, right?
I mean, you can only usually guarantee that within a single entity,
Yeah.
because I don't
Yeah,
accept time, which is
yeah,
a
it's a
weak
weak
percept.
constraint.
It's a weak
Yeah,
constraint of ordering.
yeah,
But even there, if you have to include time, I'm not sure which query will you use to actually query the event log. That's
yeah, yeah.
the.
Yeah, to be honest, yeah, you're right. The most sensible thing would be do something like having the topic publish all the events, and basically then it's up to the single
Because in
saga to,
theory, a saga in itself is a
yeah,
is in itself an event sourced
yeah,
actor, but where the consumption of events is a command. So
yeah,
you're never gonna replay that one. If you want to
yeah.
update the workflow, you will have to replay the events that the
The
workflow
events from the start.
generates,
Yeah,
but only the ones that the workflow generates, not the
yeah,
input events.
yeah,
Like the input, you have to watch one by one, and you can never restart because
yeah,
otherwise, it's as you said, you don't get any form of ordering.
yeah. Yeah, well, there are
There are
thousands
things to be
of,
figured. Yeah,
yeah, exactly. There are tons of, and I know this kind of things is also the things that maybe Johannes is happy to, uh, there these systems, get really interesting not only for backend but also for frontend because maybe when you have something that is so message driven like these systems, maybe then you can start exchange messages between backend and frontend, and maybe you can have systems where the boundaries between front end and back end almost disappear. You are messaging with an entity, who knows that if that entity is running on a client browser connected to our application or is running on the server. I can see a future where that maybe is something that we won't care about either, and we will just think about, we have behaviors that runs, and those behavior there are some behaviors that maybe run only on the browser, there are behaviors that maybe run only on the backend, but I can see a future where basically we don't think anymore about sending data through API connection. We are just thinking about
yeah. I mean, I think
actors and messages.
this is a step further from
Yeah, yeah, yeah.
RPC. Because
Yeah,
in RPC, you pretend that you're calling servers as functions. Here, you don't even want to know that they are servers. You just call things by name, and
yeah, exactly.
you message interconnected pieces
Yeah,
of your application. This is very
yeah,
interesting.
yeah, yeah. And
Good, good.
I think
I
that
I
we
think
had
we
said a
can
lot
call
of
it a day.
things. Yeah.
And thank you very much for doing this introduction.
Yeah,
Our
it was a pleasure for me.
And I guess we will shortly after this discussion move the project onto the organization so we
Yeah.
can smash it a little
Yeah.
bit and try to implement different behaviors and stuff
Yeah,
like that.
definitely. Yeah,
I can say
definitely.
that for sure. There's a lot of people interested in building these types of systems with effect.
Yeah. There are a lot of things that are raising up and a lot of things that can be built up of these kind of systems. Yeah.
And to some extent, it goes back to models like Erlang and other
Yeah.
actor-based systems. It's fun enough at the end.
Yeah.
It's all a cycle. We
Uh,
get back to
yeah, yeah, yeah. We always get back to that paper written in 1960 about actors. We
Erlang
always come back.
is the real language.
Exactly. Exactly.
Good, good.
Well,
So on that note, again, Mattia,
th-
thank you very much.
thank you
And
again for having me.
for the viewers, check out the links and everything and every reference. And well, let's give Mattia feedback and let's bring this forward.
Thank you,
Cheers.
everyone. Bye.